that we commonly come across, and that is atmospheres, millimeters of mercury, and torr. And the relationship between those is 1 atmosphere is 760 millimeters mercury, and that is 760 torr. 1 millimeter of mercury is equal to 1 torr, so it is basically a 1-to-1 conversion between them. We got into kind of the first gas law there, which is Boyles Law, and Boyle looked at the relationship between pressure and volume, keeping temperature constant. And what he saw was this relationship of P1 V1 equals P2 V2. And here again, the pressure on either side could be any unit as long as they are the same. Same thing with the volume here. It could be really any unit as long as it's the same unit on both sides. What we saw is as the pressure goes up, we see that the volume will actually go down. So we have a much smaller volume, which means gas molecules are going to have more collisions. And the result of those more collisions should result in more pressure that we see. Vice versa there, we do see the pressure start to go down as the volume goes up in this situation. And it's pretty much the opposite. As the volume goes up, it gives everybody a little bit more room to fly around in. The number of collisions is going to decrease in that case, and we will see a decrease in the pressure. Any questions on any of that stuff there? All right, so I think we laid up right here at this example, so why don't you give it a go. Sample chlorine gas has a volume of 946 milliliters at 726 millimeters of mercury. What is the pressure at 154? All right, let's take a look. So a really good approach when you're dealing gas laws. Obviously, we only have one so far, but we'll have a lot in a second. So pull out the information. So we have a volume that's 946 milliliters. We have a pressure that's 726 millimeters of mercury. We're looking for a pressure, and we have another volume that's 154 milliliters. So you can kind of see Boyle's law there, or P1 V1 equals P2 V2. You call the first set of information 1s and the second set 2s. In terms of units, we're good. Both of the volume units are the same. The pressure unit is millimeters of mercury here. So in this case, we're going to be solving for P2. So we're going to divide our V2 to the other side, and that will get us that P2 is equal to P1 V1 divided by V2. Gives us a 726 millimeters of mercury, 946 milliliters divided by 154 milliliters. Milliliters will cancel. That means the units we'll be left with is millimeters of mercury. And looks like call it here probably 4460 millimeters of mercury. Any question on that calculation there? So this is Boyle's Law relationship, so we can kind of make sure that perhaps our number makes sense. What we see when we look at the volume is the volume went down, which means we should expect the pressure to go up, and it started at 726, ended at 4,400, so it definitely did go up. So it does sort of follow what we would expect to happen in this situation. Any questions on that there? All right, try another one here. A balloon's inflated, has a volume of 0.55 liters at 1 atmosphere, goes up to 6.5 kilometers, where the pressure is 0.4. What is the final volume of the balloon? Okay, let's take a look. Once again, pulling out the information, we have a volume that's 0.55 liters. We have 1 atmosphere, which is a pressure. We have 6.5 kilometers, which is really useless information in this problem. We have another pressure that is 0.4 atmospheres, and we are looking for a volume. So once again, here you can kind of see Boyles Law, hopefully staring at you. P1 V1 equals P2 V2. We'll call these guys the ones, these guys the twos. In this case, our units of pressures are both atmospheres, so we're good to go. Once again, if they were different units, you would have to do a conversion. It doesn't matter what unit you convert it to, but they just need to be the same unit. So in this case, we're going to be solving for our P or V2. So P2 will be divided or end up in the opposite location when it goes across the equal sign. And that will go as V2 is equal to P1 V1 divided by P2. Putting in our numbers here, 1 atmosphere, 0.55 liters divided by our 0.4 atmospheres. Atmospheres will cancel, going to leave us liters as our units in this case. And we will end up with, looks like 1.4 liters in this case here. Question on that one. Once again, if we kind of look and see what's happening in terms of our pressure started at 1 and went to 0.4, so our pressure is decreasing, which means based on Boyles Law relationship, we should see the volume increase. And it went from 0.55 to 1.4, so again, it's moving in the correct direction. And that's a good way that sometimes you can kind of check your answer, because it's very common people will invert numbers and stuff like that, and gas laws divide when they should be multiplying and vice versa. Any question on Boyles Law here? All right. The next sort of relationships we're going to look at are really kind of two relationships. We're going to look at volume and temperature relationship, and we're going to hold constant pressure. We're also going to look at pressure and temperature relationship, and we're going to have a constant volume. So let's start with the guy on the right here. If we have a rigid sort of container where the volume is fixed, it will not move. We have our gas molecules inside the container. If I increase the temperature in that situation, what's going to happen is we would expect the gas molecules to be traveling faster because of the higher temperature, more energy, and moving around a lot faster. Now, because the volume is pretty much locked into place, it cannot move or anything like that or adjust. That is going to definitely lead to more collisions as they're flying around faster, and more collisions would lead to an increase in pressure. So under this type of situation, which is actually what's known as Gay-Lussac's law, is as we increase the temperature, we do see an increase in pressure because of the fixed volume. And vice versa, if we lower the temperature, our gas molecules are going to be flying around a lot slower. And because they're flying around a lot slower, the volume is fixed. That means we're going to have less collisions, and that's going to result in less pressure that's going to occur. So Gay-Lussac's relationship here is as the temperature goes up, so does the pressure because the volume is fixed. And as the temperature goes down, our slower moving gas molecules will have less collisions, and we will see a drop in the pressure. Now over here, where we look at volume and temperature at constant pressure, that's really our friend Charles' law relationship. And Charles' law basically sees this. We want to increase the temperature, for example. And if we increase the temperature, as we talked about there on the right-hand side, if the volume is fixed, then we should see an increase in pressure. But in this particular case, we actually want to keep pressure constant. So really the only way that we could keep pressure constant is the volume actually has to adjust. So as we increase the temperature, because the gas molecules are moving faster, the volume will actually increase. And because the volume increases, it gives everybody a little bit more room to fly around in. So even though they are moving faster, they now have a greater volume to fly around in. And what that does is it keeps the number of collisions relatively constant. And that's how it's able to maintain a constant pressure. So in Charles' law relationship, how it keeps that pressure constant is it's actually the volume will adjust in a way that will keep the collisions basically the same, and that will keep the pressure constant. That also means that if we lower the temperature, just like we talked about on the right there, we will have slower moving gas molecules, which means that, again, we would expect the number of collisions to start to decrease, and we would expect the pressure to start to come down. But in order to sort of maintain the same pressure, what will happen in that case is they will shrink the volume, and the volume will get smaller, which means we will still have the same number of collisions that are occurring, and that will keep the pressure constant. So as the temperature goes down, so does the volume. So it is the volume that is the key component to allowing it to maintain the constant pressure. It adjusts with the temperature in the same sort of direction to either give everybody more room so we keep the collisions constant, or squeezes everybody together to keep more collisions happening, or kind of the same number of collisions to occur. Any questions on those relationships there? And that's what we see here at low temperatures. We have a low volume and a low volume down there. And at higher temperatures, we have a greater volume, same pressure here. If you look at sort of the mercury in each of those cases at constant pressure. So another relationship that comes out of this, a very important thing, is if you do a graph like we see here of temperature in Celsius and volume for any gases you choose, what you will see is if you extend the line back to the temperature axis there, they all hit exactly at the same number, and they all hit at minus 273.15 degrees Celsius is where they pretty much all will hit. And that number should look familiar to you. That is the number basically we use to convert to Kelvin, right? So that is what we convert to Kelvin. And he recognized the relationship of this. And if you add 273.15, you get 0 Kelvin, which is sometimes referred to as absolute zero. So what that really means for gas laws is if it is temperature in a gas law, it needs to be in Kelvin. So no matter what, it always has to be converted to Kelvin in a gas law. And a reminder, hopefully you're reminded that 273 plus the temperature in Celsius will give you the temperature in Kelvin. Again, you can probably leave off the 0.15 if you like. Now, that goes for questions which are very common, sort of gas law questions, where they will give you the temperature in Celsius. They'll ask for the answer in Celsius. So people think, well, I could just leave it in Celsius since they gave it to me in Celsius. They want it in Celsius. And you cannot do that if you like the right answer. So you actually have to convert it from Celsius to Kelvin. You then have to put it into the gas law, and then you have to convert it back from Kelvin to Celsius. So sometimes people mistake those type of questions because they're asked for the answer in Celsius. They're given the temperature in Celsius. So again, they think they don't need to do the conversion. But it is 100% of the time a safe bet. If it's a gas law, temperatures involved, you best convert it to Kelvin so you do not get it wrong. All right, so let's try a couple of these here. A sample, by the way, I guess let's take a look at these laws first, I suppose. That's on the bottom there. But Charles' law is V1 over T1 is equal to V2 over T2. And once again, as we were talking about there, that is constant pressure. Once again, volume doesn't matter in this case, but temperature, as we were just talking about, does need to be in Kelvin. Gay-Lussac's law is pretty much P1 T1 is equal to P2 T2. And this is at constant volume. And here, the pressure doesn't matter as long as they are the same units. But once again, here, temperature in Kelvin. Sure, bless you. So that's Gay-Lussac's law and Charles' law, and those were the relationships that we were talking about. And again, the main thing here is again that temperature. So let's now try one that we looked at those gas laws there. A sample of carbon monoxide is 3.2 liters at 125 degrees Celsius. What temperature will the gas occupy? 1.54 liters. So give it a go, see what you come up with here. Okay, so once again, if we pull out the information, we have a volume that is 3.2 liters. We have a temperature that is 125 degrees Celsius. We're looking for another temperature here. And we have another volume. So now that we have a few gas laws to choose from, we could clearly see there's no pressure involved, which means sort of eliminates those. And clearly that looks like a winner. We'll call these guys ones, these two. In terms of the volume, we are in the same unit, so we're okay to go. But pretty much like most gas problems here, we do need to do our conversion into Kelvin for our temperature. That's going to give us 125 plus 273. It's going to be a 398 Kelvin. So now we have B1, T1, so Charles' law here. And in this case, we're actually looking for T2. That means we do need to multiply T2 to the other side and basically divide B1 back over and multiply T1 to both sides. So if I did all that there, T2 would equal our V2, T1, V1 in this particular case. And once again, things do end up on opposite sides of the arrow. So obviously that was on the bottom, that should go to the top. That was on the bottom, that should end up on the top like it did. And that was on the top, it should end up on the bottom like it did there. So basically always opposite as it goes across the equal sign is pretty much where they will end up. If you want like the quick version to rearrange. Plugging the correct things in here, we're going to go V2 up on top, 154 liters. T1, which is 398 Kelvin. And our V1, which is 3.20 liters. The liters are going to cancel. That's going to leave us Kelvin, which will be 1.54 times 398 divided by a 320. 1.92. Oh, that doesn't seem right. Try that again. 1.54 times 398 divided by 320. There you go. It's 3.2. Thank you. There it is. I'll try that again. 398 divided by 3.2 instead of 320 looks much better. There you go. 191.5 Kelvin in this case. That's a point. If we wanted Celsius, we would actually subtract 273 here. And if it would be in terms of Celsius, actually a negative number of negative 81.5 degrees Celsius. Our Kelvin didn't really specify in this case, so you can't give it in either case. In this case, we saw the volume go down, and that means that our temperature should also go down, which it did in this case. So again, that does make sense as long as you punch in the right number. I suppose that should help as well. Any questions on that one there? Okay. So let's try another one here. We have 452 milliliters of a gas in a light bulb. It's heated from 22 to 187. What is the final volume here? Okay, so once again here, we have a volume of 452. We got a temperature that goes with that of 22 degrees Celsius, another temperature of 187, and we are looking for a volume. So once again, pretty much eliminates anybody with pressure. So it's going to be Charles' law again. Here, we do need to do conversions of both temperatures into Kelvin. So we got a 460 on this guy, and looks like a 295 on that one. Here, we're going to be solving for V2, which is this. So we're just going to multiply T2 to the other side, or just move it to the opposite location. That will give us that V2 is equal to T2 V1 T1. Putting in our correct numbers here, 460 up on top, 452 milliliters, and divided by a 295. Our kelvins will cancel, going to leave us milliliters, which is a volume. So 460 times 452 divided by 295 looks like 705 milliliters. Once again, here we see our temperature increasing. So based on this relationship, we should also see the volume increase, which it does, goes from 452 to 705. So again, that is correct. And again, a good way to check yourself, hopefully, that you didn't maybe invert a number or something like that. Any questions on that one there? All right, so one more here. Argon inert gas. We have one that has a pressure of 1.2 atmospheres at 18 degrees Celsius, and it goes to 85 degrees Celsius. What is the final pressure in this case? Okay, so looking at this one here, we have a pressure of 1.2 atmospheres at a temperature of 18 degrees Celsius. We're heating that thing to 85 degrees Celsius, and we're looking for our final pressure. So once again, no volume involved, which eliminates those two. So Gay-Lussac's law is going to be the right one to choose here. Again, we could call these guys ones and these guys twos. Going to do our, like pretty much every gas law here, convert our temperature into Kelvin. So we got 18 and 273. Can give us 291 Kelvin and 358 Kelvin. So in this case here, we are looking for P2. So we need to move T2 to the opposite side. That's going to give us P1, T2. T1 is equal to P2. Putting in our numbers here, P1, 1.2 atmospheres, T2 goes up on top, divided by T1 on the bottom. Kelvins will cancel, going to leave us atmospheres as our unit of pressure, and that will get us 1.2 times 358, divided by 291 in this case. And we will end up with 1.48 atmospheres in this case. We see the temperature went up, so should the pressure, and it did a little bit. Any questions on that one there? Yeah. So again, pretty much temperature Kelvin and properly rearranging, making sure don't invert any numbers. Those are things you want to watch out for. So that's Boyles Law, Charles Law, and Gay-Lussac's law. The next sort of gas law we're going to talk about is our friend Avogadro. He had a number, but he really wanted a gas law too. So Avogadro's law is what we see there, V1 over N1 is equal to V2 over N2. And there's actually two sets of conditions here for Avogadro's law. It is at constant temperature and also constant pressure. N in this case is the moles. So N is equal to moles, which is what we associate with Avogadro's number in this particular case. So what we see with Avogadro's law is actually as the volume increases, so does the number of moles. So they're sort of proportional to each other. If you have 1 mole, you have 1 volume, basically. If you have 2 moles, you have 2 volumes of gas and so forth. And there's a couple of sort of applications of Avogadro's law, which is useful. One application is obviously like any other gas law, you can just plug and chug into the equation there and solve for whatever's missing. The other relationship is if you happen to have some type of stoichiometry problem involving gases, and it happens to be under these conditions of constant temperature and pressure, you could actually use Avogadro's law to your advantage, where you would not necessarily have to use a gas law to solve a stoichiometry problem. So if you remember, we could do stoichiometry from an equation by looking at the coefficients. And those coefficients represents either the molecules, or as we saw with stoichiometry, really the moles of everything. But if you have constant temperature and constant pressure and all the things are gases, you could actually do stoichiometry with volumes. So you could say there would be 3 volumes. one volume and two volumes, which are exact same sort of mole to mole relationship that we would use. And what this will allow you to do in a certain stoichiometry problem is you might not have to use a gas law if you're just looking for the volume of a gas that's going to be produced. You actually can just do stoichiometry with volumes rather than moles. So to show you how that sort of looks like, if we take this equation here and we have ammonia burns an oxygen to form nitric oxide and water vapor, and we want to know how many volumes of NO are obtained from one volume of ammonia at the same temperature and pressure. So we could actually do a stoichiometry problem with very limited information other than we are starting with one, for example, liter of NH3 if we wanted to. And we want to know how many liters of NO would we produce. So instead of using a mole to mole relationship, we could go this equation and have a bunch of volume to volume relationships. So we could say for every 4 liters of NH3 we put in there, we would also need to put in there 5 liters of O2. And that is, again, just the coefficients like we would do mole to mole relationship. We could also say for every 4 liters of NH3 we put in there, we would get 4 liters of NO out. For every 4 liters of NH3 we put in there, we will get 6 liters of H2O. And you can continue through all of the relationships, just like you would do a mole-to-mole relationship. So in this case, we're actually just interested in NH3 and NO, which are these two. And it's actually this relationship here. And just like we could do in a basic stoichiometry problem, we could actually use this as a conversion factor. So if we did 1 liter of NH3, using our liter to liter kind of stoichiometry from the equation, we know that we have 4 liters of NH3 will give us 4 liters of NO in this case. The liters of NH3 will cancel and we'll end up with 1 liter of NO would be produced. And again, here you would not have to perhaps use an ideal gas law or a gas law to solve this problem. So you can almost shortcut a stoichiometry calculation if you're at constant temperature and pressure, which is Avogadro's relationship, by doing pretty much a volume to volume relationship, the exact same way as you would do stoichiometry and do a mole to mole relationship. Any questions on that there? And it works for any of the things, you know, if we had 1 liter of NH3 and we want to know how many liters of H2O would we get, we would do the same sort of calculation, 1 liter of NH3. From the equation, we see we have 4 liters of NH3 will give us 6 liters of our H2O. Liters of NH3 will cancel, so basically here, 6 divided by 4, we would get about 1.5 liters of water vapor would be produced in this case. So it's a convenient sort of stoichiometry shortcut under these specific conditions, but you do have to have all gases pretty much, and you do need to have constant temperature and pressure in order to do this. Any questions on that there? All right, and obviously, like I said before, you could plug and chug into Avogadro's law and solve for any of the ones like any other gas law that we have. So some of the relationships that we've been looking at, volume decreases, pressure increases, and vice versa. Volume increases, pressure decreases, which is Boyles Law relationship. We see volume decreasing at lower temperatures, and at higher temperatures it increasing. That's Charles Law relationship, again, keeping the pressure constant. And we do see lower temperatures, lower pressures, and higher temperatures, higher pressures. When we have in a Gay-Lussac situation a fixed volume, as it does not adjust here, as you can see, this is fixed versus here in Charles Law where it's adjusting to keep the pressure constant. And obviously our Avogadro's relationship that we just saw, which basically the volume and the moles are basically exactly the same as they increase. So do this, the moles and the volumes increase proportionally. So putting all those gas laws together and those relationships gives us the granddaddy of them all, which is the ideal gas law, which is PV equals nRT. And this gas law is a little bit different than obviously all the ones that we've been looking at up until this point. First off, it's a one and done situation, which means you have one pressure, one volume, one temperature, no twos of everything sort of happening. The other important thing about the ideal gas law is it is the most restrictive in terms of units. So when you use the ideal gas law, pressure has to be in atmospheres for everything to come out correctly. Volume has to be in liters. N should be moles, and T should be temperature in Kelvin. And all those guys has to be those numbers because R is a constant that you always have available to you, 0.08206, and it has units of liters times atmospheres divided by Kelvin times moles. So the gas constant itself has all those units, and the good news is probably will be given to you, so you can always look at the units there and know what everybody else in the ideal gas law should be. I personally use this number for R. Some books will round it and use like 0.0821, which is fine as well. You should always think of R as a number that you have available to you. It is very common that they will not just give it to you in the problem. So very commonly, they won't mention anything about R or the gas constant. It's just assumed that you know that you have that available to you. So you want to keep that in the back of your mind. What makes something an ideal gas? Well, there's a couple of things that make something an ideal gas. And under most times, we do consider most gases to behave ideally. And what makes something an ideal gas is kind of two main things. The volume of the gas itself is basically thought of as being negligible. And we oftentimes will look more at the volume of the container that the gas is flying in rather than the individual volume of the gas itself. And that's why in a lot of problems, if you read them, they oftentimes will mention, hey, the gas is in this container that has this volume. And they talk more about the volume in the actual container than the gas itself flying around. The other thing that really makes something an ideal gas under normal pressures and temperatures is we assume that gases do not attract or repel one another. And what that means is you could have a bunch of gas molecules in the same container, and it's assumed almost like they're in there by themselves. Nothing else is going to interact. They're not going to interact with one another. And that is sort of an ideal gas. Later on in this chapter, we will talk about real gases where you do have to take those things into account. But under normal pressures and temperatures, you could kind of assume most things are ideal. And that's why we have this gas law, which we'll also talk about a little bit later on. But this is really more of a universal gas law for all gases under these ideal conditions. When we do have to take those two things into account, the volume of the gas and how they interact with other gas molecules, we have to get really specific about what gas we're dealing with, and there's correction values for specific gases. So in a lot of cases, most gases will behave ideally, even at a little bit higher pressures and temperatures and vice versa. They don't deviate too much until you get to really big pressures, really high pressures. You get a lot of deviation from the ideal situation. Now, a couple of other things that's important when we talk about the ideal gas law, and one thing is what is referred to as STP. STP stands for standard temperature and pressure. So when they say this is at STP, they are actually giving you both a temperature and a pressure. Temperature is 273 Kelvin. The pressure is 1 atmosphere. So in order for something to really be at STP conditions, they have to be that pressure and that temperature are the equivalent temperature pressure of Celsius or some other unit like 760 torr. If they are not, then they are not at STP. If they happen to be at STP, there is a really nice relationship that you could use, a conversion factor that you could use that can allow you to sort of bypass using the ideal gas law. And that is any gas at STP, and once again, it does have to be at STP conditions. 1 mole of any gas will have a volume of 22.414 liters. So that is a conversion factor that you can use, like I said, in place of using the ideal gas law, if you are at STP conditions, it could save you a little bit of time not having to plug things into the ideal gas law. You should never use that conversion if you are not at STP. So if your temperature is not 273 or your pressure is not 1 atmosphere, both of those together, then you should not use that conversion factor. You should use the ideal gas law. The good news is you can use the ideal gas law for any conditions, STP conditions, non-STP conditions. So if you're unsure about this conversion factor or don't want to worry about using it wrong, just forget about it and just go into the ideal gas law. You'll get the same answer. If it is at STP conditions, you just put 273 for the temperature and 1 atmosphere for the pressure. So ideal gas law you can use for any conditions. The specific conversion is used only during STP conditions. Any questions on that there? By the way, under those STP conditions, that is how we get the gas constant. So our pressure would be 1 atmosphere, our volume would be 22.414 liters, temperature would be 273, and we would have 1 mole. And again, that is essentially where the gas law comes through from, the gas constant. Yeah. Yes. So it's 760 millimeters of mercury is 1 atmosphere. That's a very common conversion. Yeah. So definitely when you're using the ideal gas law, a lot of times it's given to you in everything but atmospheres. So that's a very common conversion. Yes, to do. Yeah. Are you talking about the R constant? Is that what you're talking about? Yeah. You'd be given the R constant for this one. And this is the one that you should use in the ideal gas law. There are different values of R. There's an R value that has energy component in it, like joules, 8.314. You would not want to use that in the ideal gas law. So this is kind of specifically for the ideal gas law. Anything where you would need to use the gas constant that involves energy, you would use something like the 8.314 version of it, which is joules per Kelvin per mole and stuff like that. Yeah. Other questions? Otherwise, you have a bunch of conversions you would have to do at the end of the problem, which you wouldn't want to do, obviously. So, yeah. Other questions? Okay. All right, so let's take a look here. Calculate the pressure if we have 1.82 moles of any questions on that one? So again, we got our moles, our gas constant, and our temperature at 342.5 divided by our 543 liters gives us our 9.42 atmospheres. Let's take a look at another one here. What is the volume in liters occupied by 49.8 grams of HCl at STP? We give you some information that will be helpful. 1.008 for hydrogen, chlorine 3545 there. All right, see what you come up with. I'm looking for a volume at. Okay, so on this one, we're looking for a volume, and we have the mass here of 49.8 grams of HCl. We have it at STP. So once again, that is a temperature of 273 Kelvin. It's also a pressure of 1 atmosphere. We can get to moles here using the molar mass from the periodic table to do so. So maybe we'll do that up front, 49.8 grams of HCl. Using the molar mass from the periodic table, looks like it is 3545 plus 1.008. It would be 3646 grams per mole of HCl. That'll get us 49.8 divided by 3646, 137, 1.37 moles of HCl. So now we have our N, we have our P at T, and we're just looking for our V. So our PV equals nRT. We're going to solve for V, so we're going to send the pressure over to the other side and divide by it. Volume would equal nRT divided by P. Taking our moles of 1.37, our gas constant 0.08206. our temperature, I'll go below as I'm running out of room there. And that's going to be divided by our 1 atmosphere. Kelvin will cancel, atmospheres will cancel, moles will cancel. It's going to leave us liters. And in this case here, looks like 30.7 liters in this case of HCl. Question on that one there? Yes. You absolutely could, which is exactly what I was just going to ask, which is, could we have solved this a different way? And the answer is yes, you could have. And we could have solved it a different way, which is because we are at STP, this is one of those situations where you could use that conversion we saw earlier. That 1 mole is equal to 22.414 liters, which again will really bypass using the ideal gas law. And you could just pick it up from that point right there with your moles. And you would go 1.37 moles of HCl, and then we would use our conversion. And we will end up right there as well. So this illustrates the point. Again, if you're not sure you should use that conversion factor or don't remember it or whatever it may be, you can always, again, still go into the ideal gas law and you'll get the same answer. But in this particular case, this would be the ideal case to use that conversion since we are at STP. Questions on that there? Okay, so let's talk about one more gas law here, I think, which is also a really important one. And this is a gas law that combines pretty much all the variables together. So if we look at this one here, we can look at changes in pressure, volume, or temperature. And if we take the ideal gas law and solve it for 2 different conditions, because the gas constant is a constant value, we can basically set these 2 things equal to each other. And in most cases, if you don't open the container, the moles will kind of stay the same as they're flying around in there. And this reduces down to what's sometimes referred to as the combined gas law. And the combined gas law is P1 V1 T1 is equal to P2 V2 T2. Here, the pressure and volume, the units really don't matter, again, as long as they're the same on both sides of the equal sign. But like every other gas law here, temperature does need to be in Kelvin. I would say that this one is a really good one to know. In fact, if you want to remember this version of it, it's even better perhaps to know. And the reason for that is, since you do need to know these gas laws, and if you want to invest your time wisely, I would say you should invest it into remembering the combined gas law, the P1 V1, if you want to remember the N1 V1 version of it. So why is it good to remember this one? It's probably even better to remember it and write it correctly would be good. So put a T there on the bottom. So it would be good to remember this one because pretty much you could get all the other gas laws from this particular one. So for example here, if you had a problem where the temperature was held constant and it doesn't mention anything about moles, all you have to do is just scratch it out. And that is Boyles Law you just made. If you take this combined gas law and you come across a problem where they don't mention anything about pressure or moles, you just scratch it out on both sides, and now you have Charles' law. You could take this guy and you got nothing mentioned about volume or moles, so you could scratch those guys out. There's Gay-Lussac's law. You can look at this guy here, and if you don't see anything mentioned about temperature or pressure in a particular case, so no pressure or temperature, you can scratch those guys out, and now you have Avogadro's law. So if you remember sort of that version of the combined gas law, and you remember the ideal gas law, you pretty much have every gas law you would need at your hand. Again, you just basically scratch out what is held constant, what's not given to you, and you'll pretty much have all the gas laws that you would need. So if I were investing my time, I would remember this version of the combined gas law, and then all you have to do is scratch out what you're not using, basically, and that's held constant. You'll have every gas law that you should need. Any questions on how to do that there? Yeah. Okay, so again, you're scratching out in that case, whatever is held constant. So let's take a look at a problem here where we're going to actually use it. So if we use it here, let's take a look at one. Consider a sample of oxygen gas at 27 degrees Celsius with a volume of 9.55 liters and a pressure of 2.97. Okay, so looking at this here, if we pull out the information, we got a temperature 27 degrees, got a pressure of 2.97, and we got a volume there of 9.55 liters. We have another pressure of 8.25. We got a temperature of 125 degrees Celsius, and we have a volume that we're looking for. So again, you could hopefully see the combined gas law here. And usually people just label the first things as the ones, as long as you keep the appropriate numbers that go together. In terms of units here, our pressures are okay. Once again, if you did have some different units, you would have to do a conversion to get them to the same. We're going to add our 273 here to our temperature, and that will get us 300 Kelvin and about 398 Kelvin on that case. In this case, we're looking for V2, which means that T2 needs to go to the other side on top. P2 needs to go to the opposite side on the bottom, and that will get us T2P1V1 divided by P2T1. Again, they end up on opposite locations. Now we want to make sure we put our correct numbers in the right spots. Our T2 going to be 398 up on top. Our P1, which would be 297. Our V1, 9.55 liters divided by our P2, which is 825. And our T1, which is 398. Kelvins will cancel, atmospheres will cancel, going to leave us liters, which is a volume, so that's good. 398 times 2.97 times 9.55 divided by 8.25 and divided by 398. It is 300. Yes, it is. T1 is 300. Thank you very much. 300. Probably don't divide it by the same number. That would not work so well. So let me do that. And let me do this with the right number. So it's better, 4.56 liters. Thank you. There we go. And that would be our volume in this particular case. Question on that one there. So combined gas law, obviously we can use for changes in temperature, pressure, or volume. But also the added benefit of that gas law is, as you can see, as we just saw, you can pretty much get all the other gas laws from it. So that's kind of